Hello and welcome back. In this video, we will talk about the loss functions that we have in artificial intelligence. We will understand the loss functions in two fundamental ways. One, we will look at the elementary data in an Excel. We will calculate the loss in an Excel, and then we will switch to PyTorch, and then we will see how PyTorch calculates the same loss with same sort of data. And the reason we are doing it in twofold is because I want you to have an intuition and understanding of what is happening at the background when PyTorch calculates a loss. Because if you don't understand the basics of it, you will never understand how PyTorch calculates this loss, which also means that it will become a black box for you when you start using loss functions in PyTorch. Because as I mentioned earlier, in PyTorch, everything is basically done for you. All you need to do is you need to figure out when to use what. Therefore, it becomes paramount that you understand the basic of it, okay? So we will start with L2 loss, L1 loss, then we will take it up a notch, then we'll talk about binary cross entropy loss, then we'll talk about cross entropy loss, and as a bonus, we will also talk about KL-Divergence loss, which will become extremely handy when we design together our own chatbot using transformer architecture, okay? So make sure you watch this video in its entirety and then understand the concepts to its fullest. All right, so without further ado, let's get started. And as always, we will start with the very fundamental question that why do we need loss functions? Well, if you look at the screen, assuming this is my AI network, in general what happens is we give some input, right? And we get an output. Now, in order for this AI network to learn, we need to somehow tell this network by back propagation, right? That hey, if you're doing so, we have to tell to this network via back propagation that hey, you're doing something good or you're doing something bad. The way we calculate good or bad is by the loss, okay? Example of a loss would be that, let's say we're trying to build an AI network which will be able to predict the price of a house. Now we already know that the price of a house should be 1 million, but my model is predicting 500,000. Now there's a gap or error or loss of 500,000 between the actual and the predicted value. And this is why, and this is how we need a loss function which is appropriate for our AI application that tells the AI network which we have built that hey, if you're doing it in the right way or you're learning the right things or not. All right, perfect. So now let's go and jump to Google Colab and then see how it works. So the first one is MSE Loss, also called as L2 loss. I'm back to my Google Colab. Let me initiate it. And while this is running, let me show you what MSE loss is. So we calculate MSE loss, mean square error loss, in the following manner. So let's say my actual data is this, 9.37, 8.53, 5.29, and so on. Now this actual data could be anything. So for example, right now you see a very normal data set. Now this actual data could be anything. So right now you just see one number. This could be, for example, number of bedroom, square feet, and I don't know, washrooms. And then based on this data, my model will predict, let's say, house prices, okay? So my actual house price, let's say, is 9.73, but my model is predicting 7.23. Now similarly for a different set of bedroom, square feet, washroom, locality, XYZ, whatever data is required to basically predict house prices, my actual data says that it should be 8.53, but my model is predicting 4.75 and so on, okay? So to calculate mean square error, what you do is you take the difference of the actual and the prediction Then you take a square of the difference and then you sum it, and then you divide it by the number of observations, which is basically now mean square error. So if you go to Google and you search for MSE loss formula, if you go to images, for example, that's what you see. So we are saying that actual minus prediction, entire thing whole square, then you take a sum of all those observations and you divide it by number of items. That's what you see here. Now, how do we take mean square error in PyTorch? It's actually quite simple. So I've imported torch, and then I will just generate two random numbers, like I'll call it input and target. That's how input looks, and if I print target, that's how target looks. Now to calculate MSE loss, let me first go here and say clear all outputs, right? So what we can do is we can go to MSE loss PyTorch. Then this will take you to the official documentation of MSE loss, which is here, right? You can read about it. It's basically saying the same thing that I just explained. So this is how we will initialize the loss. So I'm saying MSE loss equals to NN package, which we are importing here, and then I'm saying give me that instance of that class. Okay. Now you might notice that I have not passed anything here as an argument, because by default the reduction is basically mean. So if you go here, we are taking the mean of everything. So that's what we are doing here. You can also provide none, or you can also provide some. So based on these inputs, the loss will be calculated differently. In general, we always go for sum of it, therefore we are not providing anything here. Okay, so if I go and calculate output and then I print output based on these input and targets, this is my MSE loss. Now if I bring the same numbers that we had on Excel, this is my x and y, then I convert them to tensors. Now if I use the same function, the output is 11.3063, which is what you also see here. Amazing, right? And the reason I'm doing it in two ways, so that you can actually understand what's actually happening when you're calculating these losses. Okay? Excellent. The other loss is called L1 loss. So we just saw L2 loss. Now let's look at L1 loss. So let's first do it here conceptually. So we have the same data set. Now I'm saying my actual data is this, my prediction is this. So the difference is A minus B, and then you take the absolute value of that. Then you take a sum of it, and then of course you take the average of it. So you divide it by the number of observations. And this is your L1 loss. Now if I go back to PyTorch, it's the same story. You can Google L1 loss like this, go to PyTorch official documentation, which is this. What you have to do is basically create an instance of this class and then calculate the MSE loss in a very simple way with a click of a button. And this is why PyTorch is super powerful. It has done all the mathematics for you. You just need to know when to use what. And hence the MAE loss is 2.9, which is also calculated here. Now there's one thing you should notice is when you calculate L2 loss, so this is also called L2 loss, and this one is called L1 loss, right? Now if you have a data set where one of the inputs could be very big, let's say 1, 2, 3, 4, now you see that MSE loss is way too much because we are actually taking a square of the difference. Whereas if you do the same thing at L1 loss, it is going up, but not exponentially growing, right? So this is where the difference between L1 and L2 loss comes in. Whenever you're deciding which loss to use when you are designing your own AI, this is the thing you have to keep in mind, that L1 is just a difference of two values and L2 is a square, which means if your data set has outlier, L2 loss will shoot up, which will basically make your AI jump all the way here and there to figure out the local or global minimum. Excellent. That's what you see here. Perfect. Now, L1 and L2 loss are great when you're doing in general regression things, but as and when your use case grow, your loss function also has to grow, right? So you have to figure out more efficient loss functions to figure out how loss is working. So for that, now let's jump to binary cross entropy loss. We normally use binary cross entropy loss when we are doing classification type of problem. When we are trying to solve classification type of problem. For example, you want to decide if the given image is an image of a cat or a dog. If the given image has, or for example, a given CT scan has tumor or not, you have to classify something between yes or no, between two classes, then you use binary cross entropy loss. The formula is this: the sum of everything, then yi log of pyi plus 1 minus yi log of 1 minus pyi. It looks a little bit difficult, but it's actually not. So if I go back to Excel and now let's think it through. So let's say this is my AI model. Now I'm giving it an image of a cat, and the way we confirm that this image is a cat by this label class. So whenever there's a 1, we have provided a cat to our model. Whenever label is 0, we have provided a dog photo to our AI model. Okay. Now if you focus on one line, now we are saying that we have provided a photo of a cat to our AI model, and my model is saying that I'm 90% sure that this is a cat. Okay. So the way you calculate binary cross entropy loss is this: yi is basically the label class, right? And p of yi is the probability of how sure your model is when it's predicting that if this is a cat or a dog, right? Now what we do here is we multiply yi and take a log of the probability. So that's what I'm doing. I'm multiplying with the label class and taking a log of the probability with the base of e, right? Now if you look at the second part of the equation, it's saying 1 minus yi. So I'm saying, okay, 1 minus my label class and then log of 1 minus the probability at base of e. If you pay attention, you'll realize that yi is always either 0 or 1, which means if it's an image of a cat, yi is going to be 1, which means 1 minus yi will be 0. And whenever my image is a dog with label class 0, that means my yi is 0 and 1 minus yi is 1, right? So that's how this works. And then I just take a sum of both, and this is how I calculate the binary cross entropy loss, which is 0.227. If you were to design this kind of formula in Python, you would do it this way. And if I take the exact inputs from the Excel, which is here, and the exact label, then I can basically run this to print the binary cross entropy loss. And again, it's the same deal that you get this object from the class of the PyTorch. And you can see it's calculating the same value. Now there's one interesting thing that happens when you do cross entropy losses. You take the log of the probability. And you might be thinking, why do I take a log of the probability? I can already see here that this is 0.9 and this is 0.1. So I already know that high probability means it's predicting right or it's predicting wrong, right? And this is where the trick is. So the reason we take the log of the probability is because the property of logarithmic functions. What I mean by that is this. I'm going to use the bocage package to plot logarithmic graph, and then you have to notice this: when x reaches to 1, y becomes 0. This is where it crosses the x-axis. And you should also notice that when the x is closer to 0, the y value is super high. Far from 0, the y value is very, very low, right? What this means is basically this. Let's take over this example. Now I'm saying that I have provided an image of a cat to my model. My model is saying I'm 90% sure it's a cat. If you look here, the loss value is 0.1, which is quite low. Now let's think it other way around. Let's say I provided an image of a cat, but my model is not able to, let's say, confidently say that it's a cat. So my model is saying I am 15% sure that it's a cat. Now notice this value goes up. Whenever my model makes a wrong prediction, this loss value goes up, and that's why we take the log of the probabilities, because we want to penalize the AI model whenever it predicts the wrong values. Okay, I hope that makes sense. And this becomes extremely handy whenever you're doing any sort of classification. All right, excellent. Now let's look at cross entropy loss. Cross entropy loss is almost same as binary cross entropy loss. In this case, we are just not looking at two classes, we are actually looking at multiple classes. So you could be looking at cat, dog, elephant, zebra, and whatnot. So the way cross entropy works is something like this. So the way cross entropy works is very simple. So if I go here, so let's say I have 4 classes: cat, dog, elephant, and let's say zebra. Okay, let's say my neural network is saying that this is the final value of all the outputs that I'm going to give you. Okay, then what we do is we raise it to the power of e. We're basically doing a softmax here. Then we just divide it by the sum of all the power to e. So we're basically normalizing everything. Once we normalize everything, now we have the classes. So we know the labels that for this value, we're looking at elephant, and this should be the right answer. Therefore, this is 1, everything else is 0. And the way we calculate cross entropy loss is this. We'll take the log of the normalized value and multiply that with the class. And you see that if current image is not of elephant, we are not bothered about the losses calculated for the non-correct classes. We only calculate for the correct class. And therefore you see a loss of 0.54 because my model is only 58% sure that this is an elephant. If I go and increase this value, let's say to 5.4, now my model is 98.7% sure that this is an elephant, and hence the loss is also went down. Okay, so this is how cross entropy loss works. You can go here and search for cross entropy loss, go to images, and this will give you the formula for calculating the cross entropy loss. So we are saying yi multiplied by log of probability of yi, right? And that's what we are doing here. And there's a very elegant thing that we are doing right now. We are saying that we take the final value, we raise it to the power of e, and then we normalize it. And you should notice that all of this becomes a percentage and the total is 1. The reason we are doing this is again because we want to use the log to penalize the wrong values, right? And whatever we did here, power e and then normalize, this both the step is called softmax. Is it called softmax? I'm not sure. I mean, there's a function called softmax that basically does this for you. So if you go back here, now why did we take the softmax? I already told you. It's basically a way of normalizing it and then use the log to penalize the wrong prediction. And there's a softmax function in the NN package. So if I run this, copy, and then I want to show you the inputs basically. So this is my input, which is exactly what you see here. And then I will pass the input to the softmax function and I'll print the input. Now you see 0.25, 0.6, 0.58. Let me copy this and bring it back here so that we can see the exact value. So the loss is 5.4 and this is the normalized value, and this is what you also see here. And as of course, if you take the sum of all of it, it will become 1, right? So this is why we take the softmax. Therefore, if you have learned something, if you have enjoyed this video, and if you want to help this channel to grow, there's one thing which is a zero cost effort that you can do today to help the channel. What you can do is basically like the video, comment on the video if you liked it, if you have any doubts, if you learned something, and most importantly, you have to share this video with 3 of your friends who you think might benefit from this video. So before we say goodbye, I have a bonus for you, as I always do. I would like to talk about KL-Divergence loss. Now this makes sense to discuss now because we are in a flow to understand what is a loss. The KL-Divergence loss will become extremely important when you and I will design our own chatbot using transformer architecture. Therefore, I would highly recommend that you stay with the video and watch and learn what KL-Divergence is. So, what KL-Divergence loss does is basically it computes the difference between the two probability distribution. It tells how similar the two distributions are. Now, the word distribution could be confusing. So, if I go here, when I say distribution, what I'm saying basically is this: a set of values like this and this, and if these values are same or not, that's all we are trying to test. So if you plot a distribution for both of this normalized value, you will get something like this. And KL-Divergence loss will test how similar these two graphs or probability distributions are. That's it. Okay. So the formula for KL-Divergence is entropy. You have already seen this. The formula is cross entropy minus entropy. If you use the probability of log, so log of a minus b becomes log of b divided by a. That's what you see here, right? And now, if you think about how KL-Divergence works, I've given an example here. Let's say we have these two distributions. So the way KL-Divergence loss will work, this will be equals to 0.5, so half, log of 0.5 divided by 0.75, which is this one, plus 0.5 divided on plus 0.5 log 0.5 by 0.25, which is 1 by 4. Therefore, the value will be 0.06. Note that KL-Divergence is not symmetric, so you cannot switch yi with y hat in the equation, right? So you have to be mindful of cross entropy and entropy, how you're subtracting both. All right. So here's the question before we call it a day for this. Is KL-Divergence loss same as cross entropy loss when we do image classification? I'll give you a moment to think about it. I will not give the solution here, but I will give you a hint. Before that, I'll pause for a moment for you to think about it. So the answer is yes, it is same when it comes to image classification or binary classification. The reason this becomes same as image classification is because in an image classification, we use one hot encoding for our label. Therefore, the yi is the actual label. It is equals to 1. So log of 1 is basically 0. And when the whole term is cancelled, right? And whenever yi is not the correct label, which means yi is equals to 0, then you're multiplying log of 1 by 0 by 0. which basically makes the entire term cancel out. So you always remain with the cross entropy. I think that's all for this video, and I will see you in the next video.